So in this lesson, we continue our discussion of population growth by introducing the exponential growth model. We see that the exponential growth model is defined by using repeated multiplication, and every term after the first term is obtained by multiplying the preceding term by a fixed amount, which is denoted by R, R being the exponential growth rate. We see in this box down below, we have the recursive definition of the model, and it looks similar to what we did with linear growth models. We still have P sub 0 that represents our initial population, and we still have a definition that uses previous data to generate new data. So the P sub n minus 1 is the previous data, and the P sub n is the new data. And then at the bottom it says where R is the exponential growth rate and R must be greater than 0. On this next slide, we expand a little bit on this R value. It is also called the common ratio, where with our linear growth models, we had a variable called D, which was the common difference. So with exponentials, we have common ratios. With linear models, we have common differences. That's something we want to distinguish between the two models. And if the common ratio is unknown, then we can take the next term and divide it by the previous term in order to find out what R is. Similarly, we can redefine the recursive model and express it explicitly, as you see here. We are now using something that looks like function notation. And we explored this previously, saying that function notation allows us to jump straight to the population of any generation we want. If we want to know the population of P10, we can plug it in and get that answer. Where with recursive models, we would have to find P1, P2, P3, all the way up to P10. So we like the explicit model. It allows us to accomplish our work more efficiently. So in this first example, we are asked to find the population of the first 5 generations using this model. At first glance, we should see that this is a recursive model. So P0 is already given to us, but now to find P1, we would take that number 1 and plug it in everywhere we see an n. So that would tell me P1 is equal to P0 times 3. And then we get our P0 by referencing the old data and plugging it in. So now we can say that P1 is equal to 16 times 3. And we get that P1 is 48. So we can do this again for P2. We would plug 2 in everywhere we see n. That tells us that P2 is equal to P1 times 3. We would look up our answer for P1. We see that our answer for P1 is 48. So we would plug that into P1. We get 48 times 3. And we get 144 as our value for P2. Again, with P3, we would plug in 3 everywhere we see the n. We would get P3 equals P2 times 3. We look up the value for P2, it's 144, so it's equal to 144 times 3. 432. And then for P4, we have P3 times 3. We look up the value for P3, multiply it by 3, and we get 1296. So that's generating population data using the recursive model. In this example, we can generate population data using an explicit model. So to get P0, we would plug 0 in where we see n. We see that with the function, there's only one n showing up here. So we get 2 times 4 to the 0 power. Anything raised to the 0 power is 1, so we have 2 times 1, and we get that P0 is equal to 2. Now we don't need previous data to get new data. If I wanted to, I can go straight to P4. And I would plug in 4 where I see the n. It would be 2 times 4 to the 4th power. And 4 to the 4th power is 256, so we have 2 times 256. And that gives us 512. So we didn't need to generate 1, 2, and 3 to get to 4. But with the recursive model, we would have needed all of the in-between data in order to get to the 4th generation population. And we can continue this with the rest of these. So we have 2 times 4 to the 1st power, we get 8. 2 times 4 to the 2nd power, we get 32. And 2 times 4 to the 3rd power gives us 128. Here we're just asked to convert a recursive definition so that we can have an explicit form of the model, and then we want to find P4. So the formula was P0 times the growth rate to the nth power. So for this example, we can say that P of n is equal to 11 times 5 to the nth power. And then when we were asked to find P of 4, that would be 11 times 5. Oops. P of 4 is equal to 11 times 5 to the 4th power. And that gives us 6,875. What if we were not given the initial population? How do we solve for it? Well, we take the data that we have here, and we said first we have to get our R value, and once we have our R value, we can work backwards to P0. So since we know P3 and P4, we say, well, the R value is equal to the next term divided by the previous term. The next term is P4, the previous term is P3. So R is equal to P4 divided by P3. We can say that R is equal to 81 divided by 27. We get R is 3. So since R is 3, that means we multiplied P0 by 3 to get P1. We multiplied P1 by 3 to get P2. And we multiplied P2 by 3 to get P3. Since we know the value of P3, we can plug it in and we can work backwards. So P2 times 3 is equal to 27. But if we divide both sides by 3, we get that P2 is 9. Now we can plug this into the previous line. P1 times 3 is P2, which we just found out was 9. If we divide both sides by 3, we get that P1 is 3. And now we can find P0, which is the initial population, multiplied by 3 gives us P1, but we just found that P1 is equal to 3. If we divide both sides by 3, we find that P0 is equal to 1, and that is our initial population. That's what the question was asking us to find. In this example, we see that our data is 3 generations apart. From P4 to P7 is 3 generations. So if I divide 256 by 32, I won't find R. I'll find R applied over 3 generations. So we can say that R raised to the 3rd power is equal to 256 divided by 32. And again, I got this 3 from the 7 minus 4. Those are the subscripts of P4 and P7. So now we want to take this 256, we want to divide by 32, and we find that R to the 3rd power is equal to 8. And now we want to take the cubed root of both sides. So the cubed root of R cubed is equal to the cubed root of 8. So we find that R is equal to 2. That is our growth rate for our exponential model. Now we just need to work backwards from P4 to find out what P0 is. P4 is equal to 32. If I divide by 2, I'll get P3, which is equal to 16. And if I divide by 2, I'll get the 2nd generation, which is now 8. If I divide by 2, I'll get the 1st generation, which is 4. And divide by 2 one more time, and we get the initial population P0, which is 2, and that's the answer we're looking for.